Alright guys, this is going to be the Battlestar Galactica calculation. The problem is that the actual BSG is in my classroom hanging from the ceiling, so all I've got are these. Okay, so the calculation is similar to this, but of course in the real calculation they're looking for Earth. Oh, wrong way. Looking for the Earth, maybe like somewhere right around here, right around there. But in my calculation, as usual, I'm going to use Mars as a stand-in, or as Schwarzenegger would say, Mars. I'm going to use Mars as a stand-in. Okay, so this calculation should help you figure out how to do the BSG calculation, the Battlestar Galactica calculation. It really like squishes your brain. It's really like a brain problem. And even though this is not exactly what you're doing in the Battlestar Galactica calculation, it's similar enough that if you watch this example, you can figure out how you would do it. Remember, I gave you weird units like cubits, for example, right? But in this example, I'm going to use weird units like feet. Like some guy's foot, they decided to make that a unit, and it's stuck for all these years. So anyway, we might not realize that feet is a weird unit, but it kind of is. Anyway, so notice how I'm going to have to do conversions just like you're going to do there. The only main difference is that you're going to be starting off with a velocity, and I'm going to be starting off with a period. Okay. Also, I want to just give a plug for tau. Remember that tau is more fundamental than pi, because you notice how you always have to use 2 pi? So why use 2 pi all the time, like here and here, okay, when you can just use tau, just one constant. So it's really just the value of 2 pi. So instead of being like, 3.14159265359 times 2 equals, it's 6.28318530718, and so on. So we could just use the 6.28. Maybe I'll use the 6.283 part. Just use one extra digit this time. But I think tau will supplant pi eventually if the wind blows its way. It is hard to change things in mathematics and science, but if you think about it, isn't going from the radius all the way to the circumference more fundamental than going from the diameter to the circumference, which is what pi is? So anyway, someday, maybe I'm a dreamer, tau will supplant pi. Okay, well look at these equations, for example. See that one? Look how much cleaner it looks with tau. See that one? Look how much a little bit cleaner it looks with tau. So for the purposes of my calculations, we'll still talk about it in terms of pi, but just remember that 2 pi is tau. Okay, so I might just directly write in, I think I'll just directly write in 6.28. Just remember that's 2 pi, which is tau. Okay, I'll put in 6.283. So I'll put that right here. Tau equals 6.283. No units. It's just a unitless factor or ratio. So here we go. The moon Phobos orbits Mars at a distance of 3.08 times 10 to the 7th feet. Phobos' orbital period around Mars is 7 hours and 39 minutes. Okay, like Donnie Darko. Determine the mass of Mars, then find the gravitational acceleration of Mars, then calculate how long it would take a rock to fall 36 feet on Mars. Isn't it cool that we can do that? That's what I love. I love that there is this equation that you can actually figure out the mass of a planet just by looking at something going around it. And you don't even need to know the mass of the orbiting body. You don't even need to know the mass of the moon or satellite. So you just look at something going around and you say, oh, look how long it takes to go around. Look how far away it is from the center. We got the mass, we've taken the mass of the planet. It's like we've weighed the Earth. Now, it's not really weight, it's mass. But it's like weighing something, if you want to use that incorrect terminology, using an object just going around it. And we use this all the time. Like, let's say there's a black hole at the center of our galaxy, which there is. Well, we can tell what its mass is just by looking at a star going around, telling what its orbital period is, and its distance from the center. We can find the mass of that invisible object. It's amazing. We don't even need to have the orbital period. We could just get the velocity of it and use that in conjunction with this. If we know the circular velocity and we know the distance, we can find the period. And that's what you're actually doing in the real Battlestar Galactica calculation. Okay, so what are we going to use here? Because we have the distance that the moon is orbiting and we have the orbital period, we are going to use this calculation right here. We're going to use this to find the mass of Mars. By the way, Phobos and its partner moon Deimos, Phobos and Deimos, Fear and Panic, are the two moons of Mars. They're not like Earth's moon. Like Earth's moon is more than a quarter of the Earth's diameter. Like it's pretty big. It's like a moon of Jupiter. Oh yeah, it'd be like this brain. It'd be like, yeah, about like that. So the Earth's moon is about like this brain. And of course, it's much further away. Okay, you go around the Earth 10 times to get the distance to the moon. You know, it's like 250,000 miles away. But it's pretty sizable compared to the planet. It almost makes us a binary planet, by the way. Except the center of mass is only 1,000 miles below the surface of the Earth. About 1,600 kilometers below the surface of the Earth. Okay? Mars's moons, on the other hand, are like little potatoes. They're like little tiny little asteroid things going around Mars. If you saw them going around from the surface of Mars, it would look like, I don't know, like a little space station in the sky. No, nothing like the Earth's moon that lights up the Earth at night. Okay, so what have I got to do here? Well, we're used to using metric, and G is in metric units, obviously. Oh, I don't think I've ever seen G in standard units. That would be funny, right? I also toyed around with the idea of defining some units so that G would just disappear. Like defining some units of like, redefining, let's say like the kilogram, so that G would not be necessary. Because people think that constants are like fundamental and important, but really they're just a fudge factor for the way we've defined our units. So if you did define the kilogram based on this equation, G could magically disappear. Anyway, I think kilogram would be the easiest one to use here to do that. But anyway, aside from that, let's just keep rolling with the regular old-fashioned metric system. Okay, or new-fashioned metric system. Okay, so we're going to turn this into metric, all right? So in order to turn this into meters, we need to know how many feet are in a meter. And remember the difference between a meter stick and a yardstick? Well, here is a meter, okay? A meter is the length of this entire ruler up to there. And a yard would get you to right there. That's 3 feet. So notice that the difference between a yard and a meter is very small, but it is significant. It is appreciable. So obviously when the French guys in the French Revolution were designing the meter, they were clearly going for something that was about a yard. You know, something you could hold in your hands, something that was smaller than the human body. So it's no surprise that it wound up close to that, okay? But because there is a little difference, it turns out there are 3.28 feet in 1 meter. 3.28 feet per meter. So the first thing I'm going to do is I'm going to take the 3.08 times 10 to the 7th feet, and I'm going to multiply it by the conversion factor. And the conversion factor is, I've got to put feet on the bottom, so 3.28 feet and 1.00 meters on the top. It's very close to 3.28. I think the next digit is even a 0, or it rounds to a 1 or something. Okay. So then basically we're dividing this by 3.28. This helps you remember whether to multiply or divide. That's the main reason we use these conversion factors, or we write them out formally. So remember, like, oh yeah, so the feet are going to cancel. Feet divided by feet equals unity, and it disappears. And then I can just take the 3.08 divided by 3.28, and obviously that's a little bit less than 1. That gives me 0.939, okay, and then it's times 10. Well, this doesn't change, 10 to the 7th. And now we have meters, okay. So obviously this is improper, so I'm going to correct it over here, equals 9.39 times 10 to the what? Move it over once this way. So instead of 7th, it would be 6th. 10 to the 6th meters. So now that is the distance that Phobos orbits from the center of Mars, okay? Presumably, it doesn't give me any more information here, so we're assuming this is from the center. If it wasn't, we would need more information. We would need like the diameter of the planet and add that to it, but presumably that is from the center of the planet, because that's the only number we're given. Okay, so that's the same as this. Okay, so maybe I should just write it next to there in case we need it again. 9.39 times 10 to the 6th meters. We've converted that to metric. Okay, the next thing we want to do is we want to turn this time into seconds. Now it's interesting that the metric system, even though they were all radical and crazy, chop off king's heads, get rid of the old units, they really didn't mess with time. Other than changing the calendar back to year 0, well, that really didn't work because we still call it 1789 when it happened, so we don't call it 0. But they really didn't try to make the clock decimal because this system goes all the way back to the Mesopotamians, the way they counted to 60, and they just decided, let's not mess with that. Okay, so we're going to turn 7 hours, 39 minutes into seconds. Now, I'm going to write 7 hours, I'll just write the word, 39 minutes. Now, 7 hours, let's turn that into minutes and then add it to 39 to get the total minutes. That's the best way to do it. So obviously because of the Mesopotamians and the way they counted up to 60, there are 60 minutes in an hour. So I'm going to take 7 times 60, right? That's 420. And then I'm going to add the 39. I'm just going to go ahead and add the 39. Plus 39, and that gives me 459 minutes. And then also because of the Mesopotamians, there's 60 seconds in each minute, so then I can just multiply that times 60. If you want to see the conversion factor, it would be like this. It would be 60 seconds in 1 minute, right? And then the minutes would cancel. I didn't bother writing it for that, because I think you guys know that. And then what we get is 27,540 seconds. Okay, so now we have things in meters and seconds, and you know how we usually want meters, seconds, and kilograms as our units. Just remember those are the ones that typically come up in most situations. Okay, oh, we better put that in scientific notation. Well, then the decimal would go there. It'd be 2.75, I'll just forget about the 4, times 10 to the, what would that be? Think about how many positions we would need to move it. 1, 2, 3, 4. So it'd be 10 to the 4th seconds. So now, next to this, I could write 2.75 times 10 to the 4th seconds. So now that we've converted these things into the right units, we can begin our calculation with the orbital period. Okay, so we're solving for, what are we solving for here? The mass. So we've got T, but let's just write it in. Let's just go ahead and write it in. Which one of these is my T? Remember what T stands for? T stands for the period. It might help if you think of time period, if that helps you. So which one is it? It's this, right there. This is my T. So I'm going to put that in place of T, right? Orbital period, okay? So I'm going to put 2.75 times 10 to the 4th seconds. That's this. And then I'm going to write equals, okay? And then 2 pi or tau, okay? And what did we say it was? 6.283? 6.283. We'll just use one extra digit there. Now, that is 2 pi, right? It's also tau. Okay, so don't get confused by that little part. Then we've got the Teenage Mutant Ninja Turtle radical function and a little fraction bar inside there. And on the top, we've got r. Oh, I think we just got r, right? The moon orbits at a distance of, so that's not a diameter, that's the distance away from the center of the planet. That's a radius right there. So that is r. So we can just put that in. I think I'll use a different color since I already used purple for that. I'll use 9.39 times 10 to the 6th meters. But remember, that whole thing gets cubed. It gets cubed. All right. And then on the bottom, we've got regular old G, okay, the universal gravitational constant, our old pal, 6.674 times 10 to the negative 11. And in this case, we're using the units meters cubed per kilogram second squared. Now, sometimes you see different units on that, depending on whether it's using newtons or if anything else is involved. You can change them around, but it always winds up equaling these fundamental units. And then what we got here is what we're solving for, m. That is the mass of Mars. Oh, I probably should have made that red. Oh well, it's a dirty planet. I'll make it brown. I'm sure there's some brown dirt on Mars. It's not all hematite. It's not all hematite. Okay, so now notice what we're doing here. We've got to, and by the way, there's no units for a unitless factor or ratio. Okay, so now we got to get that solved for. Oh man, it's in the denominator? Under a square root? Oh, come on, right? Makes it a little tricky. Okay, so the next step, what we're going to do is we're going to cube this, and I'm going to rewrite it here. I guess I'll just rewrite the whole thing with this cubed. I guess that's the only step I can really do at this point. Oh, you know what I'll also do at the same time? At the same moment I'm cubing that, just to save time, I'm going to go ahead and, doctor, this is multiplied onto me. Oh no, I'm afraid we're going to have to divide that off. So we're going to divide both sides by tau, okay, or 2 pi. So if I do those both at once, it'll save us one step, so why not, okay? So I'm going to take, let's see, I'll write it over here, 6.283, right, divided by, and then I don't know where to fit it over here, it's hard to fit it, I'll just put it right there, 6.283, you can do that. And then of course, this is going to achieve unity with the universe, it's going to go bye-bye, and this is going to give me my new left side of the equation. So let's do that part first, 2.75, okay, divided by 6.283 equals. Now it's 0.4377 if I rounded it. So the only problem is it's less than 1, so I'm going to need to move the decimal. So let me just write this over here on the side before I write my next line. It's going to be like 0.4377, right? Oh yeah, but I'm going to have to move the decimal back 1. Okay, and then it's going to be 10 to the 4th, but if I move the decimal back 1, what would it be? 10 to the 3rd. So I'm going to write 4.37, I'll just keep these 7s for now, times 10 to the 3rd seconds. Do you see what I did there? I moved the decimal back 1 and corrected the exponent. Okay, so I've divided those, this disappears, and now I've got this equal to just the radical, what's under the radical. And we're cubing what's under there, okay? So obviously it's going to be like 9 cubes, and I'm trying to think if it was 81 times 9. It would be like 750 or something, so I'm thinking it'd be like 800-ish something like that. Okay, so 9.39 times, and then of course if you hit equals and then equals, that's cubing it. Because every time you hit equals, it does the function again. Okay, yeah, so 827. And I know that that's reasonable because I did that little estimate in my head, and those aren't always great, but at least I know sort of like what it's going to be. So I know it's not a crazy answer, so it's probably the right answer. So I'm going to put, oh yeah, let's write this over here. 827.9, right? And then 10 to the 6th cubed. Oh, you know what to do when you cube something with an exponent with the same base? Well, it's like multiplying these numbers. It's going to be 10 to the 18th, right? Because 10 to the 6th times 10 to the 6th times 10 to the 6th would give you 10 to the 18th, right? However, I have to move the decimal over 2 more places. So before I write it here, I want to get it in proper scientific notation. So obviously, if I move it over twice like that, it's going to go up to what? 20. So I'm just doing that on the side to save some space here. So I'm getting 8.28, now I'm going to round it to there, that 9 rounds it up to an 8, times 10 to the 20 meters cubed. Meters cubed or meters cubed, right? Okay, and then we still have the same denominator. We haven't altered the denominator yet, right? So we've got 6.674 times 10 to the negative 11 meters cubed per kilogram seconds squared times Mars. Mars's mass. Okay, so at least we got rid of some things now. We've neatened it up. Okay, now to do the next line, I think I'm going to have to bring in another piece of paper. What we're going to do is we're going to divide these. That'll be the next step. Okay, so notice these two numbers, and I'm going to be dividing them. Okay, so now, because we still need these to use these numbers, I just folded a paper here so that we could transfer them up. So we've got 4.377 times 10 to the 3rd seconds. I probably could have rounded that at this point. Equals the square root of, so now what I'm doing is I'm dividing these. I'm going to divide these, and whatever I get is going to be the numerator, and it's still going to be over m. So notice when I divide these, I'll get a single number, and then it's still going to be divided by m. So I'm just going to write it like this. Oop, this one doesn't work. I'm going to write it like this, and put the m underneath. How about that? Okay? See, m is still in the denominator. Okay, so first of all, if we divide 8.28 by 6.674, 8.28 divided by 6.674, what I get is 1.2. Oh good, it's a number that's in the ones place. That really makes it easy for us. Okay, so I'll write this one in purple. 1.24, and then I got to deal with the exponents. So 10 to the 20th divided by 10 to the negative 11, oh boy. So remember, you can think about it like a subtraction problem. Think about it as like 20 minus negative 11. Oh, that's like 20 plus 11. What does that equal? 31. And so that'll be my new exponent. Okay, it just follows the rules of addition. It like goes down a notch. Instead of, when you're really multiplying, well here you're really dividing, you go down a notch to subtraction. And when you're multiplying, you go down a notch to addition, right? And then what's going to happen with the units? Well, look, meters cubed divided by meters cubed. Those are going to disappear, right? And then we're dividing by per kilogram second squared. So those are going to wind up as being the units on the top. So it's going to be kilogram second squared. Okay? Does that make sense? Okay, the next thing we need to do is we need to shed this radical function. We need to de-radicalize this equation. The only way to do that is to square both sides. Okay? So if I square this side, I'll get that. And if I square this side, this will just magically... So the camera just shut off, And what I just did was, I took the square of both sides, I corrected the scientific notation, okay? By taking the square of this side, it just gets rid of the square root. It's everything that was under the square root is now out because it's been squared. That's what a square root means. And then I'm getting ready to cross multiply, so I threw this over a 1 so that this would be a fraction and this would be a fraction. So remember, when you're cross multiplying, look for the two numbers that are diagonal from each other. 1 is one of the numbers. So these two are diagonals. Those get multiplied. But then again, multiplying by 1 doesn't change anything. So we just get this. And then we look for whatever number doesn't have a partner. This doesn't have a partner diagonally because that's an unknown variable. So that's the one we divide by. It's cross multiplication and then division, and it gives you your unknown no matter where it is. So I'm going to rewrite this like this. I'm going to write it, I guess I'll fold this down to here. I'm going to rewrite this as m equals, so this times 1, okay, is that. So that'll be my numerator, 1.24 times 10 to the 31st kilograms seconds squared. And that's going to be divided by the leftover number, the number that isn't partnered with anything, okay? And that will be my 1.92 times 10 to the 7th seconds squared. Doesn't that make sense that the units would look like this? Okay, so remember, I like to cross multiply. The other way to do it, of course, is you multiply both sides by m, get m on this side. Then you divide both sides by 1.92 times 10 to the 7th seconds squared, and it winds up there anyway. It winds up like this anyway. I just like to cross multiply. It's just my thing. I just love it. Okay, so now when we divide these, obviously the number is going to be less than 1 because the denominator is larger. So when we divide these, let's do it. 1.24 divided by 1.92. And again, I'm just going to write that off on the side because I'm going to be correcting the scientific notation. So I'll put 0.6458. I'll just put all those numbers. And then we got to deal with the exponents. Well, 10 to the 31st divided by 10 to the 7th, oh, that's just like 31 minus 7, right? 31 minus 7, and that equals 24, right? Let's just double check. 31 minus 7, 24. 10 to the 24th. And then what units? Well, the second squared cancel. That equals unity, disappears into the universe. Kilograms. Oh, of course it's kilograms, because look what we're solving for. The mass. Better be kilograms, right? So now I'm going to put that here as my final answer for this one. I'm going to put it in proper scientific notation. 6.46, I'm rounding to the hundredths place, as I typically do, times 10. Oh, if it goes back that way, so if this was 24th, that would be 23rd, and the unit would be kilograms. So that is the mass of the planet Mars. I could even write sub M or sub Mars here if you want. That's the mass of Mars. Isn't it cool that you can determine the mass of a planet just by looking at a moon whizzing around it and how far away it is and how long it takes to go around? I love this equation. By the way, what is this number? 6.02 times 10 to the 23rd particles. This is Avogadro's number. So notice, the mass of Mars in kilograms is slightly larger than Avogadro's number, the number of particles in a mole. Cool, right? So that is the answer to determine the mass of Mars. So let's write it up here. The mass of Mars, I guess I'll keep it in brown. So M Mars equals 6.46, I almost wrote Avogadro's number, times 10 to the 23rd. I think I could remember this one. Kilograms. Now, what are we going to do with that? Well, the next thing we're going to do with that, which is something we've kind of done before, in fact, I think I've done this exact example before, we're going to use that to determine the gravitational acceleration of Mars. little g. We're going to do this. So this equation, all it requires is the mass of Mars, okay, and we need the radius. In this case, the radius of Mars. So I got to give that information as well, okay? So we're going to need the radius of Mars, not the orbit of this moon, but the radius of the planet. And we're going to use the mass of the planet that we just determined. That's all we need to determine the gravitational acceleration. Like here on Earth, we know what it is, right? But we need it from Mars in order to do this last calculation. Okay? So I'm going to replace these papers, but now that we've got the mass of Mars right there, we're going to use it in our next calculation. Okay. Now that we know the mass of Mars, okay, we are now going to find the gravitational acceleration of Mars using this equation. This is a modified version of the universal gravitation equation, okay, to find the local acceleration. Now, in order to do this, we need the radius of Mars. Here's the radius of the planet, not the radius of the orbit of Phobos, the radius of the planet, but it's in kilometers. So we got to turn this into meters. So I think I'm just going to do that over here. And let's see if it's 3.390 times 10 to the third kilometers. Oh, I probably shouldn't have put it way over on the side like that. Okay. Then how many meters will it be? Well, there's obviously, you're going to divide by kilometers. It's obviously going to be 1,000 meters in 1 kilometer. And that equals 10 to the third meters in 1 kilometer. So it's this times 10 to the third. So it's going to be 3.390 times 10 to the sixth meters. Okay? So the radius of Mars equals 3.390 times 10 to the sixth meters. Notice how if I multiplied this times that, the kilometers would cancel and we'd be left with meters. Okay? So that's what we need here. And we've already got g, it's the same old g. And we're solving for the little g. We're solving for the little g of Mars, the gravitational acceleration. Now we're used to using that on Earth, but now it's going to be the planet Mars. Okay, so it equals, oh, both of these are bad. Okay. And now we're going to put in the universal gravitational constants. I guess I'll also put that in green. 6.674, using this again, times 10 to the minus 11 meters cubed per kilogram second squared. Okay, so that's the g part. And then I've got my little fraction bar here, a little fraction bar, and on the bottom I have this. So why don't I just go ahead and write that? 3.390 times 10 to the sixth meters. Oh yeah, but look, squared. It's another example of the inverse square law, okay? Comes up a lot. And on the top, you've got the mass of Mars. Oh, like right there. I'll just transfer it down right here. 6.46 times 10 to the 23rd kilograms, okay? And that isn't squared or anything. So what I'm going to do is I'm going to multiply these two as together, because the g might as well be in the numerator, right? And square the denominator. I'll do that all at once. I'll do that in one step, just to save a little space. So the little g of Mars is equal to, oh, these are running out. I'm going to multiply these two. So obviously 6 times 6 is 36. I expect something, you know, more than 40 in that range. 6.674 times 6.46 equals 43. Okay, this will be my numerator. 43.11 times 10. 10 to the negative 11 times 10 to the 23rd. Oh, that's like 23 minus 11. That's like 12, right? So let's just double check. 23 minus 11. Of course, it's 12. And then the kilograms, of course, are going to cancel here. Okay, so what we'll have is meters cubed per second squared. Okay, that's in my numerator. You know what? For now, I'm just going to leave that improper. I didn't write that off to the side. I'm going to leave that improper there. Because maybe when we divide it, it'll save us a step. Then I'm going to square this. Now, 3 squared is 9, so this is going to be something like 10, more than 10. 3.39 times 3.39, 11. Okay, so that seems reasonable. Okay, I get 11.49. Now again, this is improper scientific notation. 10 to the 6th times 10 to the 6th, 10 to the 6th squared, 6 times 2 is 12. That makes sense, right? Because 10 to the 6th times 10 to the 6th, you would add them, it'd be 10 to the 12th. Meters squared or meters squared, of course. Now notice that because I've done both of these in improper, when I divide them, it should put me back into proper. Let's see if that works. I might have saved myself 2 steps by not putting it in proper. I'm just going to go ahead and write it here, since the little g of Mars equals this, equals that. Okay, so 43.11 divided by 11.49 equals, good, it's a single digit number. Okay, so it worked out for me after all. 3.75, and it's going to be times 10. Well, 12 minus 12, what does that give me? 12 minus 12? 0. Isn't that funny, right? Sometimes that happens. Okay, and then meters cubed divided by meters squared gives me meters, and then nothing affects the per second squared. Well, that's what we'd expect for an acceleration, isn't it? So look, we got the acceleration on Mars. Let me rewrite that. Let me put it over here. Okay, the g of Mars equals, I guess I gotta write it below, 3.75 times 10 to the 0 meters per second squared. So that's a lot less than Earth. Obviously, that's about 1/3 of the gravity on Earth. The gravity on Mars is much less, so accelerations are much slower. They never seem to get that replicated in movies. Like even The Martian, where they put that huge budget into that movie. What really bugs me is they didn't show the lower gravity. Just show it! That'd be so cool! Okay, so now that we've got the gravitational acceleration of Mars, guess what? That's this answer. Boom. We already have this answer, the mass of Mars. So we need one more answer. Calculate how long it would take for a rock to fall 36 feet on Mars. Well, 36 feet, you know. We got to turn that into the metric system. We got to turn that into metric units. Okay. So if we've got 36 feet, okay, and we've got 3.28 feet per meter, so now we're going to have to multiply this by the conversion factor, right? And the feet have to go on the bottom. Now, 3.28 feet per 1.00, if you want to do that, meter. So we're basically dividing. That just reminds me that I have to divide, in case you get confused by that, okay? So then, my black is running out. 36 divided by 3.28 equals 10. Okay, I guess I'll just write this in what color? 10.98 meters. Okay, if I want to put that in scientific notation, 1.0, I think I'll keep the 98 though. 0.98 times 10 to the first meters, if I wanted to put that in scientific notation. But that is my height, okay? I think I'll just go ahead and use this one when I'm dividing, okay? I think I'll just go ahead and use this one. Okay, so that is the height we want it to fall. Now we're talking about falling, not throwing it down, not throwing it up, just falling. Oh yeah, so what do we need for that? Vertical motion equation. Remember this one? So it's starting at a height of 10.98 meters. We'll make that positive. That's the initial. it's going to end at 0. So I'm going to put that over here. I'm going to go ahead and write that in green. Now, by the way, I guess I should separate these calculations with a line here, maybe. That would be good. Okay, so now we're doing this last one. Okay, so y final will be the ground, 0 meters, equals y initial, 10.98 meters. I'll just keep it not in scientific notation. Plus its initial velocity. Well, it's falling, so 0. This whole term disappears. Plus 1/2, don't forget the 1/2, g, but this is the g of Mars, right? And the g of Mars is 3.75 times 10 to the 0 meters per second squared, right? Times t squared, okay? And that's what we're solving for, t, right? Okay, the only thing is here, guys, that because we've defined this height as positive, and heights are measured above the ground positively, that means that the gravitational acceleration, which is toward the ground, is going to be negative. So don't forget, if you define something as positive, that determines whether the gravitational acceleration is positive or negative. Now, we got to get this on the other side, subtract both sides, subtract 10.98 meters from both sides, and what we get is negative 10.98 meters equals 1/2, and then we've got Mars's g, 3.75 times 10 to the 0 meters per second squared. We could have just put 3.75 meters per second squared times t squared, okay? So then we're going to need to move it up one more time, I think. One more time. The only problem when I folded it up, I had to move this. Okay, so now we're going to take 1/2 of Martian g, so that's 3.75 times 0.5, or divided by 2, same thing. And it's still going to be negative, but it's going to be negative 1.875. I think I'll just keep those. And again, 10 to the 0 isn't changing anything, but I'll just keep it in that form. Meters per second squared. That's 1/2 of Martian g, t squared, and that is still equal to the negative 10.98 meters. Okay, doctor, this is multiplied onto me. I'm afraid we're going to have to divide it off. So if we divide both sides by negative 1.875, 10 to the 0 meters per second squared, then obviously this will achieve unity with the universe. And then over here, dividing by 1.875 times 10 to the 0 meters per second squared. But when we divide negative by a negative, I get a positive, okay, which is what I would expect. This is like dividing 10 by 2. I expect something around 5. So 10.98. I never put the negative signs into the calculator, by the way. Divided by 1.875, and I get 5.856. Okay, so I'm going to write that as 5 points. I'll just write all of this, 856. And then, well, the problem is I just divided something without an exponent by something with an exponent, okay? But remember, if you do that, you keep the same exponent, 10 to the 0, okay? You could have thought of this as, even though it would be improper, we could have thought of this 10.98 times 10 to the 0, okay, divided by 1.875 times 10 to the 0. It's going to give you 10 to the 0, right? 0 minus 0 equals 0, okay? Okay, so then meters divided by meters. When we divide by per second squared, they wind up on the top, so it's seconds squared, and it better be because it's equal to t squared. So now we've got to take the square root of both sides, and obviously that's going to give me t. I think I'll have to write it over here, t, and when we take a square root, it's technically equal to plus or minus the value, right? So 5.8 856, okay, square root, and I get 2.419. Now I think at this point, I'm just going to round it to the hundredths place. 2.42. And then, oh, what happens when we divide 10 to the 0 by 2? Well, doesn't change it, does it? Now remember, taking the square root of numbers in scientific notation, you want to have this as an even number. But with 0, it doesn't matter. It'll just be 0 divided by 2 still gives you 0. Okay, so is 0 really an even number? You can debate that all you want. And then the square root of seconds squared, we get seconds. So the time it would take for something to fall 36 feet on Mars is 2.42 times 10 to the 0 seconds, which of course is 2.42 seconds. And that is the answer. Now we usually put it in scientific notation, and that's my final answer here. So then, if we wanted to know, is this really the ancestral home of the colony, or maybe the Cylons? Are they Martians, like if they weren't from Earth? You know? Then we would check this against the scrolls of Pythia. Okay? So this is very similar to what we're doing on the Battlestar Galactica calculation, with the one exception that you were starting with the period instead of the velocity. So the only really additional step that you need to do is take the velocity of the moon and the radius of the moon's orbit and turn that into a period. And once you got that, you pick up from where I started. And the rest of it is very, very similar, and it's a similar calculation, something falling off the opera house. It's given in like cubits instead of feet, but obviously turn it into meters, and then find out how long it takes. And so that would be my final answer. Let me write that next to here. Okay, so that would be 2.42 times 10 to the 0 seconds. That would be, now by the way, you might wonder, well, what about the plus or minus? Well, that's assuming the symmetrical trajectory, that how much time, if it had started on the ground and gone up to that point, okay, how long before you started would it have left the ground? It would have been at 0, assuming a symmetrical trajectory. That's why it gives you plus or minus. But since we don't know if that's what happened, we just know that it's at 36 feet, the minus doesn't really mean much. So we would use the positive value here. We would use the positive value. 2.42 times 10 to the, that's a 0. That's a 0 if you can't tell. Okay. Seconds. All right, so that's how you do the Battlestar Galactica calculation. That's how you can tell, is it the Earth? Is it really the Earth? So good luck. I know it's not easy. Hang in there. So say we all. So say we all.